All right, welcome back. This problem here is, it says you have a 40 kilogram beam, it's a uniform beam, and is 5 meters long and rests on the supports shown, or as shown. A 20 kilogram boy walks along the beam. How close can he get to the right end of the beam without it falling over? Okay. As you see, there are supports here. If the boy stands here, there is no risk. As he walks this way, there is a risk that the beam will tip over, meaning it will lose contact here. The moment it loses contact, you see this support applies a normal force on the beam, and this support also applies a normal force on the beam, as long as they are in contact. When the beam tips over, it means it loses contact here, and then the force will be zero. That normal force will be zero. So this is support 1, so it's applying force, normal force 1, and this is support 2, and it's applying a force, normal force 2. And I'm talking about the force on the beam. The beam is 5 meters long. By the way, they say this here is 3. Right? So this is 1 meter, 2 meters, 3 meters, 4 meters, 5 meters. So the center of mass of the beam is halfway, so that's 2.5. So the gravity will pull down on the beam with an mg. And then you got this boy who is standing somewhere here. The gravity will pull on the boy with an mg, but the boy doesn't fall over because the beam applies a normal force on the boy. By Newton's third law, the boy applies the same normal force back on the beam. That normal force has to equal to the weight of the boy because he's balanced. So that is the weight of the boy times gravity. Okay, so now we're going to say the net torque has to be 0, because otherwise, if the net torque is not 0, the beam will rotate. And since the beam will rotate probably about this point, you're free to, it's static equilibrium, so you're free to take the point of rotation anywhere you like. This is a good point to take it. So we will take the torques about that point and see what happens. So let's say the sum of the torques must equal to 0, because there is no acceleration. And so the torques consist of the torque due to normal force 1, plus the torque due to the weight of the beam, plus the torque due to the support 2, plus the torque due to the boy. And they have to add up to 0. Now, if the boy is at this critical point, the beam is about to lose contact. So this normal force, N1, is arbitrarily close to 0. So we just say the limit as n goes to 0, so it's just contributing 0 torque. So this one is 0. The torque due to the second support is equal to 0 because we're taking this as the point of rotation, or as the pivot point. And this normal force is at 0 distance from itself, and therefore it contributes 0 to the torque. Now, the beam itself, the weight of the beam is a distance here at 0.5, and so the torque it will contribute about this point, it's trying to rotate it counterclockwise, so that's a positive torque. And as usual, the torque is equal to the distance from the point of rotation. The distance is 0.5 times the force itself, which is mg, mass, times gravity. I will substitute with the mass in a moment, times the sine of the angle between the arm length and the mg. And so that's 90 degrees. Sine of 90 is 1. Sounds good. Now, the boy is applying a force this way, and that force will try to rotate the beam clockwise, so that's a negative torque. How far is the boy from here? Well, we don't know. I'll just call it r. We're trying to figure it, actually. And then the force by the boy is the mass of the boy times gravity, his weight, mg. And then times the sine of the angle that the position vector makes with the force vector, and that's a 90-degree angle. So sine of 90 is 1. So you get 0. And so set these equal to each other. So 0.5 times capital M times G will equal to R times little m times G. G's cancel. And so R will equal to 0.5 capital M divided by the little m, which is the mass of the buoy. So 0.5, the mass of the beam is 40 kilograms divided by the mass of the buoy, which is 20 kilograms. And that is, well, half of 40 is, so this is just 1 meter. So the buoy would have to be 1 meter this way. So how far from the right is he? Well, this is 3, the beam is 5, so this is 2 meters. He walked already 1 meter this way, so it's 1 meter away from the, so 1 meter away from the right. If he's at 1 meter, is about, if he takes just one little step, he will tip over. Walks back, he's fine. I would like us to look at this following problem here. Let me get my calculator and get my pen here and try to explain what's going on. So you have a pulley here. You got a mass of 2 kilograms, and a 4 kilogram mass. And you probably can guess what happens. The 4 is heavier, so it will fall, and then the 2 kilograms will rise, right? 2 kilograms will rise. I'm going to, so this is the 2 kilograms. So the pulley will start to rotate. The pulley here, it's a solid disc, and it has a mass 2 kilograms and a radius of 0.06, and it rotates about its center, so about its center of mass, and so it has a moment of inertia. So as this mass falls, it accelerates downward. As this mass rises, it accelerates upward. They have to have the same acceleration, otherwise you have slack in the strength. On the other, and then as the pulley rotates, there is frictional torque. So if it rotates this way, the torque is actually clockwise. It's clockwise, so that because it's friction opposes the motion. So it's you might as well put a minus sign here because we'll assume it will go counterclockwise, which is positive. We will assume clockwise is negative, counterclockwise is positive. Sounds good. Now here's what I want to show you or argue to tell you that this tension here, let me call this one here T1, and the tension here is T2. So on the pulley, tensions always pull. So this tension T1 will act on the pulley here, T1. And it's acting at 90-degree angle to this. And then T2 will act this way on the pulley, T2. Now, tension 2 must be larger in magnitude than tension 1. Remember when we had ideal pulleys, these two tensions were equal. And they were necessarily equal because if the pulley had zero mass and it was an ideal pulley, then if the two tensions are not equal, if one of them is larger, then you have a torque. And a torque on a zero mass will cause an infinite angular acceleration. So you're saying the pulley will spin infinitely fast, even though the masses will not have infinite acceleration. So that's incorrect. So the tensions had to be balanced. However, when the pulley has mass, so it will have an angular acceleration. If there is an angular acceleration, there has to be a net torque. This tension here is trying to rotate it clockwise, and this tension is trying to rotate it counterclockwise. So the torque due to this one wins. So there is torque due to this one and torque due to this one. And which one wins? It's this one. So it will contribute a net torque, and therefore there will be an angular acceleration. I hope that's clear. So when you have a pulley and it's not massless and so on, then the two tensions are not going to be equal. Okay, so I hope I convinced you. So now let's go to the sum of the torques equal to I alpha. The net torque will equal to I times alpha. In here it's I about the center of mass. The net torque, there would be torque due to tension 2 and it's counterclockwise. Let me call it torque due to tension 2. And then the torque due to tension 1, that would be negative. In a moment I'll put the minus sign. And then plus the torque due to the friction. They have to equal to I alpha. I times alpha. So the moment of inertia, it would be that of the pulley. So 1/2 the mass of the pulley times the radius of the pulley squared times alpha. This is the moment of inertia for the pulley. The torque due to tau 1 would be force times distance times the sine of 90 degrees. So it would just be tension 2, however much it is, times r, the distance from the point of rotation is r, and then times the sine of 90 degrees, which is 1. This is causing clockwise torque, and so that's a negative tension. So it would be tension 2 times r, tension 1, not 2. Tension 1 times r. And then plus the torque due to friction, and that's negative 0.5. Negative 0.5. Because it's, if the motion is this way, then the torque would be that way. Equals to 1/2. The mass of the pulley is 2 kilograms. So 1/2, 2 kilograms. The radius of the pulley is 0.06. I'm going to leave that as let me see. I should have used capital R here. So let me just leave it as the radius of the pulley squared times alpha. Let me just leave it as our pulley. For a moment, I will leave it like that. So this is just 1. So you get T2 minus T1 times R minus 0.5 will equal to alpha times R is the acceleration, and then times R, right? The acceleration, because it's the tangential acceleration, right? As the pulley spins, the string is released, and it's released at a rate, if it's going without slipping, R times alpha. So R alpha is an acceleration, but I have R squared, so this is just R times the acceleration. And the 2 and the 1/2 cancel. So I just have R times the acceleration. And yes, all right, so that's good enough. I'm trying to do it the easiest way possible. I will leave this for a moment here. Okay, let's now go to this mass here, and then this mass here. So for this mass here, I have what are the forces on it? Tension upward, and then m2g, the 2 kilograms times gravity downward. So I have T1 minus 2 kilograms times g downward will equal to, it's accelerating upward, so it's equal to ma, so it's 2 kilograms times the acceleration. So T1 will equal to 2g plus 2 times the acceleration. Yeah. And then, so let me box this one. How about T2? For this one, you got T2 upward minus 4 kilograms times 9.8, so 4g will equal to the mass times acceleration, but this one is accelerating downward, so it's negative 4 times the acceleration. And again, the accelerations have to be equal. When this one rises by an inch, this has to drop by an inch, and the pulley has to turn accordingly. So T2 will equal to 4g minus, when you move it to the other side, minus 4a. That's T2. So I will go here and substitute. So let's see what this gives me. What is T2 minus T1? So it would be 4g minus 4a minus 2g minus 2a. So 4g minus 2g is 2g, so let's do it quick. T2 minus T1 will be 4g minus 2g, that's 2g, and then minus 4a minus 2a, because you're subtracting, so you have minus 6a. So I'm going to come here and substitute this. So I have here 2g minus 6a times r minus 0.5 is equal to r times the acceleration. Let's divide both sides by r. So I have 2g minus 6a divided by r, the r goes away, minus 0.5 divided by r is equal to just a. Here, just a. Move the 6a to the other side, so you get 7a. So you have 7a. In here I have negative 0.5 divided by r. Let's substitute the r now. It's 0.06. And then 2g. This one we moved it the other way, so it became 7a. So 2g, so 2 times 9.8. And so the acceleration will be, so you do this and then divide by 7. So let's find it. So I have 2 times 9.8, that's 19.6, and then minus 0.5 over 0.06, that gives me 11.2666, and then divide the whole thing by 7 to get A. So I get 1.61 meters per second squared. Let me just double check and make sure I have it correct. Yeah, 1.61, that's the acceleration. And I think and the question is, how long will it take this mass to hit the floor? I mean, the acceleration is downward, and it has to fall by 1 meter. Y initial is 1, Y final is 0, and the acceleration for it is 1.61, but downward. So we say, all right, Y final equals to Y initial plus V initial times the time minus 1/2 of that acceleration times the time squared. The minus is because the acceleration for the 4 kilogram is downward. Y final is 0, Y initial is 1, V initial, it starts at rest, so that one is just 0, and then minus 1/2, the acceleration is 1.61, and then t squared, and so you get t equals to, what? Where is my calculator here? I get 1.115. Let me just double check. Yeah, approximately 1.1. Okay, 1.115 seconds. Right, good. So that's that. Let's see, we might do one more problem. Yeah, 17. Yeah, let's do one more problem and end this. All right, this next problem here involves a little bit of calculus. It says a rod of length L and capital M and mass capital M, so these are given, has non-uniform mass distribution. So the mass distribution is non-uniform. The linear mass density is lambda equal to some constant c times x squared, where x is measured from the center of the rod and c is a constant. The first question is, what are the units of c? And then find c in terms of L and M, and then find the moment of inertia about an axis through the center of the rod. So this rod here is non-uniform, and so here is the rod. Let's draw it. It has length L, and we're measuring x from the center, so let me choose this to be the x-axis. This is the y-axis. So it gets heavier as you go on. So basically this rod, when x is 0, the density is 0, so it has no mass in the middle, and then it gets heavier as you move out. So the question is, what are the units of this constant? Well, first of all, if you look on the left side, this is the linear density, so it's the mass per unit of length. So the left side has to be kilograms per meter. Here I have c, the units of c. And then what are the units of x squared? The units of x squared are meters squared. So let's divide both sides by meters squared. So I get the units of c will be kilograms divided by cubic meters. Those are the units of c. They would be kilograms per cubic meters. So we answered the first question. That's just dimensional analysis. Okay. So now, what is c in terms of L and M? I know that the mass of the rod, the rod weighs mass capital M. So what is C? I know that the mass, a little mass dm, a little bit of mass dm will be lambda times dx, right? If I take a slice here of thickness dx, it will have a mass dm, and that dm will depend on lambda. So if I integrate both sides, the integral of dm is just the total mass. And here I have to integrate, where is the mass found? It's found between negative L over 2 to L over 2, because the whole length is L, so this is minus L over 2 to L over 2. So minus L over 2 to L over 2. And then lambda is C x squared, and then dx times dx. So this is an even function, so this is just twice the integral from 0 to L. So I get capital M will be twice the integral from 0 to L, from 0 to L over 2, just twice. And then C x squared dx, and the integral of x squared is x cubed over 3, so you get 2/3 C x cubed evaluated between 0 and L over 2, and that's equal to M. And therefore, I get M will be, when you substitute L over 2 and you cube it, it becomes L cubed over 8. And so L cubed, so 2/3 C L cubed over 8, right? The 8 comes from the cubing of the half. And so I have here 24, and there is a 2, so 1/12. So you get 1/12 C L cubed. So what is C? Therefore, C will equal to 12 M divided by L cubed. And the units do make sense because kilograms mass over length cubed, which is meters cubed, so it's length kilograms per cubic meters, as it should be, which we got earlier. All right, so now what is the moment of inertia about this axis? So imagine you take this rod and you spin it about this axis. So what would the moment of inertia be? Well, remember the moment of inertia, let me write with a different color here. The moment of inertia will be, is the integral of x squared dm. X squared dm. So I have the integral of, well, the mass is found only between minus L over 2 to L over 2, and then x squared. And what is dm? Dm is lambda dx, and lambda dx is cx squared dx. So cx squared dx. And so we get x squared times x squared is x to the 4th power dx minus L over 2 to L over 2. And the c itself is 12m over L cubed. So it's 12m over L cubed. And so, again, this is an even function. X to the 4th is an even function. So it's just twice the integral from 0 to L over 2 of x to the 4th dx. So this just becomes twice. So twice this is 24 m over L cubed, integral from 0 to L over 2 of x to the 4th dx. By the way, you could just integrate this and then substitute the lower and the upper limit, but it's a pain because why would you cube and subtract twice? It's just easier to, the lower limit will be 0 and it just goes away. Just double it. And so let's continue. So I get I will equal to 24m over L cubed. Let's see, what's the integral of x to the 4th? Well, it's x to the 5th over 5, evaluated between 0 and L over 2. X to the 5th. And how much is this? Well, let's see. 24 capital M divided by L cubed. When you substitute, I have to divide by 5 here. There's Now, L over 2 to the fifth power, that's L to the fifth power, and 1/2 to the fifth power gives me what? 32, right? 2 to the 3 is 8, 16, and 32, yeah. And then the lower limit is just 0. And so this becomes what? 32, we can divide, so first of all, L to the fifth, L to the third, that's just L squared, and the M is here. And then let's see, if we divide 32 by 4, that gives me an 8. Divide this by 4, you get a 6. Yeah, divide this by 4, you get by 2, you get a 4. And you divide this by 2, you get a 3. So you get 3 over 5 times 4 is 20. So 3 over 20? Let me make sure I didn't make any mistake. Yeah. Actually, yeah, I got it. That's good. All right. That's the end of this. And I will see you in the next chapter, which is... what's the next chapter? I forget, actually. Newton's universal law of gravitation. All right? So it would be like planets and all that stuff. All right. See you.